All right, so today's lecture, we're going to start going into some of the image correlation analysis. And I know on the Slack channel, I think I sent out a video link that had kind of a basic understanding or basic description of how we can apply cross-correlation analysis with our image analysis to identify regions that are similar. And we're going to, today and on Thursday, we're going to take this approach and apply it toward a particle image velocimetry analysis of a TIFF stack. So to give you an idea of what the goal is here, this video is from my PI at Florida, Tom Angelini's lab, where they're looking at the kind of the motion of an MDCK monolayer over time. And each one of these red arrows is a velocity description of where that frame or kind of that region of interest within the video is moving and where the relative intensity increases from the cross-correlation analysis. So as I hit play here, you can watch as the cells and the cells in the model layer kind of fluctuate their motion. You see the changes in the velocity as indicated by the length of the arrows growing larger and larger. So this is kind of the basics of particle image velocimetry. It can give you ideas of regional interest of increased velocities, flow, vortices within your images as well. Just kind of that sort of analysis. So that's our goal today, is to write some code that does this process. And to do that, I believe in the Dropbox as well should be a link to the week 3 notes as well as 2 images. I'm just also going to post them in chat as well. If you give me a second here. Yeah, so today we're just going to start and look at just these first 2 images and compare to them. And I forget exactly what they are, but they should just be some wave images of 2 subsequential frames from a movie. So as soon as Fiji loads here, we can take a look at it. Actually, might be just faster in Matlab. Yeah, there we go. So here's our first frame here. And we see it's kind of a wave pattern going on. And we'll open up a second figure and take a look at data 2. So you can see, because there's subsequential frames from our video, they look relatively similar, but there's some slight changes in the location of our kind of the crest of our waves. So down here you can see it's started breaking into 2 separate ones. The entire image is shifting from the top right to the bottom left. So we're going to try to be able to capture and try to determine what the magnitude of this change in position is across images. To do that, we're going to use the cross-correlation analysis. And we're going to use the Wiener-Kinsham theorem for calculating the Fourier transform of a function of time, and then calculating the cross-correlation by taking the Fourier transform of one image multiplied by the Fourier transform of the other, and then taking the inverse Fourier transform of that. Okay, so in Matlab, we can quickly calculate the Fourier transform of any function using the FFT function. And I think it stands for just fast Fourier transform. And how this kind of works is we're going to start by just creating some dummy function. In this case, we'll say we just want to create a sine wave from, say, 0 to 5 times pi. If remember, if we put in between our starting and ending values, we can specify our time step. So here we'll do 1/100th of a second. And then we'll define y as just the sine of the sine at each time point. So as we expect, if we just plot what y is, it should just be our sine wave. And then what we can do is just take the Fourier transform, FFT, of that function, and we'll call it here f of y for Fourier transform. And you see, we now have the Fourier transform. It's a complex double. And if we actually wanted to take a look at it, we can just plot the real portion of our Fourier transform. And we get kind of this misleading graph. On the left, as we go across, we see this huge spike. It's a positive values, a negative spike, and then it kind of flatlines, and then the same thing on the far right-hand side. So the reason these spikes are at either limit of our image here is because as Matlab does its fast Fourier transform process, it kind of works its way to the right across your vector and then back toward the left direction as well. So to correct this, we're going to use this function FFT shift. And what this does is it will shift your zero frequency components of your Fourier transform back to the center of your graph. So right now, we go back to our plot. We kind of work from 0 to positive frequencies, and then from negative frequencies back down to 0. So by using the FFT shift of our Fourier transform, we're going to redefine that as just our Fourier transform again. And then we're going to again plot just the real component of our shifted Fourier transform. And now it kind of matches up of what we'd expect. So if we were to zoom in here on the center of our Fourier transform, we see two peaks, and these peaks should correspond with the frequency of our plot. The other thing you can see, our x-axis isn't quite correct either. We're just plotting a pixel space. So we can quickly correct that by saying our frequency should be equal to, just gonna copy and paste it here real quick, kind of our negative value, or half our negative value to our half our positive value times our time step. In this case, our time step was 0.1. Oh, not CYY, FY. And now if we plot our frequency versus our the real portion of our Fourier transform. Yeah, there we go. We can see now that our kind of zero frequency is right at the center here of where we'd expect it to be. And then hopefully, if we did this right, it's still off. I'll have to come back and figure out what exactly is going on there. I will get an answer to that because I'm missing something when we're correcting for our frequency axis. But anyways, so that's how we can calculate the Fourier transform of a function. Similarly, to take the inverse Fourier transform, we can just use IFFT. So if we do IFFT of our Fourier transform, and we'll call this IFY for the inverse Fourier. We can then plot the same thing. And we'll see we should recover I didn't like that at all either. Oop. All right, guys, I swear to God, I just checked this before I logged on and it was working fine. Well, all right, I'm gonna have to go back and double check what I'm doing wrong here. But we can use the inverse Fourier transform to calculate the inverse Fourier transform of our Fourier space to get back into real space. So how are we gonna use this for our correlation analysis? If you watch the video that we posted on the Slack channel, we saw that the Fourier, or the correlation function between two functions can be defined as your Fourier transform of your function in time space times the Fourier transform of your next function. In this case, we'll call it g of t. And then the inverse Fourier transform of all this. Okay? So to do this in Matlab, we're going to follow the same kind of nomenclature. We're going to take the FFT of our function. So in this case, it was y, lowercase y. And then we're going to multiply it by, in this case, our second function, if we want to do the autocorrelation, or comparing the same image to itself, or the same data set to itself, it would again be the FFT of y. And here, to make sure we're in real space, we actually want to multiply this by the complex conjugate. And this takes into account the convolution theorem of calculating the cross-correlation function. So to take the complex conjugate of an array, we just use conj, C-O-N-J, of our vector. So now we have the Fourier transform of our function y times the complex conjugate of our Fourier transform of y. We then want to take the inverse Fourier transform. And then the last thing we're going to do is we're just going to add in that FFT shift. So that way we correct for our zero frequency being in the center of our plot. And here we're going to call this CYY. This stands for, in my nomenclature here, just the correlation function of y and y. And then one last kind of tidbit that we need to add in here for our plot is when we're using the FFT functionality in Matlab, there is a slight discrepancy between its values and the analytical solution. And we can correct for this by just dividing by the length of your data set. And I think in my notes, I go into a bit more detail of where this comes from, but mostly when you calculate FFT, it's missing the discrete time interval between the time step between data points. So when we take the Fourier transform, we get a dt here. When we take the Fourier transform here, we get another dt. When we take the inverse Fourier transform, we get a d omega. And then we can do kind of a definition of what d omega is as 2 pi over the length of our data set times our time step, to simplify it down to just this length here. All right. Oh. And of course, because we're multiplying a vector by another vector here, and we want to multiply each element within the vector by its corresponding element in the second one, we add our period here. And now, if we were to plot what our CYY is, sorry, same thing. We want to we can see when we have zero shift in our function. So the 0 point here is the center point where we're kind of basically overlapping the image on top of each other. We have a maximum correlation. And something's funny here. Hold on 1 sec. There's just something funny here. This maximum value should be a 1 because we are at the kind of the center location. FFT y times complex conjugate divided by the length. Yeah, I don't know what's going on there either. Anyways, all right, so my point is, at zero shift in our values, we see we're at the kind of maximum correlation. Our images match up nicely. And as we shift it through tau, we can see our correlations kind of decrease and decrease and decrease. When we get to some point, we're at the negative correlation. So we're kind of anti-correlated with our function. And then it increases back up again as we kind of step through our frequency of our sine function. One second, I'm just. Yeah, I don't know what's going on. But anyways, so that's how we calculate our correlation function. All right, so we're going to use this correlation function to kind of step through our regions of interest in our video frame to determine where that peak location is. So we go back to our plot here, where this peak location occurs at. And we'll say where it's at is that's where these two images overlap the highest. And that's kind of the idea of where that image is moved between the individual frames. So to give you kind of another example of, if we define y as the sine of x, and we'll call z is equal to the cosine of x. And we can again use this kind of correlation function and do the cross correlation between our y function and our z function by replacing our second variable here. So now we're taking the FFT of y and multiplying it by the complex conjugate of z to get the cross correlation between y and z. And if you were to think about this, right, now at a zero time shift or zero lag shift, we no longer expect these images to overlap perfectly. And instead, and when we look at the cross correlation function, that's what we see. At the zero time lag, our images no longer overlap. In fact, they're not correlated at all, which is what you expect between a sine and a cosine wave. But as you slowly shift your image through some time lag, there's a location where there's a maximum correlation, right? And this is kind of, when you think of a sine wave, this should be what, pi halves, I believe, right? And as you keep shifting back, it goes to no correlation, and then to negative correlation, back to positive correlation, and so on and so forth. So if we were to look at this image, we could say, well, here, our peak correlation value occurs at some shift in our, or some lag shift. In this case, it corresponds to like 1.4. Any questions on how we're going to calculate the correlation function? All right. So if not, we'll start going through our code here. And I'm going to kind of start from scratch so we can just work through it together. So the very first thing we do, obviously, is just kind of read in our data. So again, we're going to use the imRead function of our image as a TIFF file. So we're going to read in our TIFF file. We're going to convert it into a double so we can do our mathematical operations on it. And we're going to do the same thing for our second image. So data 1 and data 2 should be our two images that we want to compare. The next step, we need to define a box size or a region of interest. And what this will do is tell us kind of the maximum size we want to look for where within our image are we the same. We don't want to compare the entire image, that's going to slow down. And if we have a very high sampling rate of our image, we expect the movement to be relatively small. So here, we're just going to say our box size is about 16 pixels, and our overlap between boxes is going to be about 10 pixels. So again, we can then just use basic math and say, well, the spacing between the center of any box should be our box size minus our overlap. So that tells us every 6 pixels, we expect the center of a new box. And then using this spacing, we're going to determine what the total number of rows and the total number of columns for our boxes is going to be. All right, and we can do this by saying, well, we know the size of our data in the x direction is size of data 1. If we subtract the box size, that way we're not getting our box covers this full part of the image, and divide it by the spacing. I'm going to throw some parentheses around here. Yep. It should tell us how many boxes fit within our row. And then if this isn't an integer value, we can get some weird results because we can't have 2.5 boxes in our image. So we're going to use this function floor. And what floor does is just rounds any value n down to the closest integer. So the floor of 2.5 is 2. 2.75 again is 2. So we're just going to round down to the closest number of boxes that fit within our box space. And then we can do the same thing for the number of columns, but use the second dimension of our data 1. Okay, so now we know how many rows and how many columns of boxes we're going to have within our image. And to do this, we're now going to set up 2 for loops where we basically step through every location and then compute the autocorrelation analysis at that box location. So we can think of, for our columns, start with rows. For rows are 1 to the number of rows. And then we'll do a nested loop for columns equals 1 to the number of columns. We're going to enter in some code, and then we're going to close our for loops. So what this does is steps through each one of the rows, and then for each one of the columns, and then at that row and column, we expect to have a box. Does it make sense so far? All right. So now that we're at this location, what we want to do is first just figure out where our pixel location of the center of our box is. So we'll say what row our center is at is equal to box size divided by 2, and then plus our spacing times whatever row value we're at. And we want -1, so that way, because we start at row number 1, we want box size just to be halfway across, right? So you can imagine our box size is 16. So we're running in our first row. Our spacing is 0, but our box size is going to be, or our box center is going to be at 8, right? 16 divided by 2. And we go to our second row. We now have that same 8 plus 1 spacing. And then in the next row, it's plus 2 spacing, so on and so forth. We could do the same thing for our column. So now the location of the center of our box and the column side is again your box size, but now instead of row -1, it's going to be column -1. So this here tells us where the center of our box is. All right, now that we have the center of our box, we want to, we're going to create kind of just an outline of where our box is, or just a vector for which rows fall within our box and which columns fall within our box. So we'll call that for sub row. And that's just, again, going to be our center location minus our box size to the center location plus the box size over 2. I think we just want to add 1 here just to be safe as well. And then the same thing with our sub columns. So now it's, instead of row C, we're going to be column C. And same thing over here. All right. So this tells us what rows and columns fall within our box. So let's take a second here. I'm just going to highlight and save these into our workspace here. And then as an example, I'm just going to declare that we're going to look at the first row in our first column. So we're just going to, instead of using our for loops, I've defined row and column as 1. We can see where we ask where the center is. The center of our first row for our first box is going to be at 8. Our column is also going to be at 8. And then our sub rows should be 1 through 16 against the size of our box. And then our column should be the same thing, 1 through 16. All right. And then finally, we want to grab the actual data that corresponds to that location. So we'll call this sub data 1 from our first image. It's just going to be data 1, kind of our very first frame. And we're going to grab our sub rows and our sub columns. And we'll do the same for sub data 2. And both these lines of code then just set up subdata 1 and 2 as regions of interest within Tim, for Matlab, 1 is the first index. All right. And we got 7 minutes left. We can keep going here. So we've now defined our subdata that we're interested in. The next thing we want to do is we want to normalize this data. And we want to normalize it such that it has a mean of 0 and a frequency of 1. So we're just going to shift our data by subtracting the mean So we're going to calculate the mean of all of the values within subdata 1 and subtract that from our matrix. And then we're going to divide by the standard deviation of all the subdatas, of all the elements within that matrix. So if we look right now, we have a mean currently of 26 and a standard deviation of 7. After we normalize it, if we look at our mean value, our mean is now effectively 0, and our standard deviation is 1. And we're going to do the same thing for subdata 2 as well. Okay, And now that we've normalized, when we've taken our data and we've normalized it, we can go ahead and compute the cross correlation function. So we'll call it correlation function. If you remember, we calculate this from the Fourier transform of our first function times the complex conjugate of the Fourier transform of our second function. We then compute the inverse Fourier transform of that result. And we want to shift it back so our origin's at 0. Now, the one difference here is because subdata 1 and 2 are a two-dimensional matrix, we're going to actually use this function FFT2 and IFFT2. And what this does is just tells MATLAB we want to compute the Fourier transform in both the x direction and the y direction. All right. So we can go ahead and highlight and run that. Conjugate. And now let's go ahead and take a look at what that image looks like. So we can see kind of in the center here, we have this yellow line. So if we look at those values, they're going to be close to 1, or doing me the kind of the peak values. And then as we go across, they get lower and lower. Oh, I did forget one thing. Again, because we're computing the correlation function, we do have to divide by the length of our data sets. So in this case, the length in our x direction is the size of our subdata 1. And then the length in the second is the size of subdata 1 in the second matrix size. There we go. All right. So let's quickly, before we run out of time here, I'm going to grab a different row and column here. Hopefully we could. So right now I've just hard coded in the 5th row and the 7th column. So and we're going to take a look at that correlation function. Oh, still not good. Oh, there we go. All right, so we're at the 5th row and 5th column. We can see now that there's like a distinct peak of where our maximum correlation location's at. So we're 8 by 8, that's our center pixel, it's the center of our square. But we see the actual location of maximum intensity is over here on the right, where our value is 5.3 or about 5.3 or so. So that's telling us between these two frames, the location where these two boxes or regions of interest look most alike are actually when they've been shifted, in this case, about whatever that is, 5 pixels. All right, and we have less than a minute, but when we get back after our kind of quick break, we're going to talk about how we can use peak fitting functions to determine this location and then plot that on top of our curve and just get kind of the distance we've traveled between frames. All right, so I will see you guys in a minute here.